back. This is unit 6.2 now, and this is called stoichiometry. In your reading, please read pages 404 to 432 in your book, and in your study guide, that's going to be pages 170 to 182. Well, the best way to explain stoichiometry is by comparing that to a recipe. So here we have a recipe for chewy sugar cookies, and when you look at recipes, it usually tells you how much can be made in the recipe. So this one tells us we can get 76 cookies out of this if we follow these instructions. So it tells us the amount of ingredients to use, and if you'll notice that it is in cups, in teaspoons, and in units, like individual units, like 4 large eggs. So supposedly if we combine these together in a certain order, like number 1, mix the butter, the sugar until creamed together, the dry ingredients in a separate bowl, etc., and we bake these at 177 degrees Celsius for 10 to 12 minutes, we're going to get 76 cookies. So just like a chemical equation, when we combine things together, the chemical equations we just finished talking about, that we get certain products. For example, if we mix the 2 cups of butter and 2 cups of sugar, the 4 large eggs, and the 2 teaspoons of vanilla, we're going to get what the recipe referred to as the wet ingredients. And if we mix the flour, the salt, the baking powder together, we're going to get what's referred to as the dry ingredients. And if we take our wet ingredients plus our dry ingredients and apply heat, and in chemical equations, you usually have to provide some kind of heat for a reaction to happen. Well, what happens with these cookies is the materials that we mix together, the heat does cause a chemical reaction and produce cookies. All right, so stoichiometry is the same process. So I need you to pause the video and write down these steps, because these are the steps that we're going to use in these chemical equations. All right, and I did put a note down here. Some people can set up their conversion factors as they go, as they're solving the problem, and some people like to have them already set up before they start the problem. And I'll work it both ways just to show you, so you can choose whichever way is more convenient for you and fits your learning style. Okay, so let's use the recipe that we have for some simple stoichiometry. So our first question is, how many eggs will I need to bake 114 cookies? Well, let's use glues. What's our given here? Well, our given is going to be 114 cookies. So I'm going to go ahead and write that down. Okay, and we need some kind of relationship from our chemical equation, from what's given to us, from our recipe. We need some kind of equality that can get us from cookies to eggs. So let's look back at our recipe. Well, what's the relationship between cookies and eggs? Well, the recipe tells me here 76 cookies will take 4 large eggs. So those things can be equal. That's equal. If I have 4 eggs and I mix the rest of this together, I can get 76 cookies. So remember what we said when we're doing conversions about equalities. Equalities can be used to set up conversion factors. So if 76 cookies is equal to 4 eggs, I can make that a fraction, a conversion factor, okay? And I can put 4 eggs on top and 76 cookies on bottom. It doesn't matter, one over the other, just however I need to use it. All right, so if I have my problem, the given there, I'm going to put it over 1. Now I'm going back to conversions. So you may need to brush up and review on those steps that I give you for conversions. So I have my given, 114 cookies. How many eggs is this going to take? So the question mark is how many eggs? So I want to set this up so that when I cross out my units, I want to have eggs left over. All right. So in a recipe, a lot of times, if you are good at cooking, or if you've ever cooked before, sometimes we can look at this and say, well, I can double my recipe, right? If I double my recipe, how many cookies am I going to get? Well, if I get 76 cookies out of one recipe, if I double it, all I have to do is add these together. Okay, so I'm going to get 152 cookies if I double this. Well, I don't need 152 cookies. Let's just say that baking these cookies for a party and all I need is 114. I don't want all of these cookies left over that I'm going to have to eat, because then I may gain some weight and I don't want to do that. So if I only want to bake 114 cookies, what measurement of ingredients am I going to need? All right, so we have cookies set up over 1. So in order to get rid of cookies, I'm going to have to put it in the bottom here. So if I'm following my steps, I'm asking myself, what unit do I want to get rid of? The answer is cookies. Where do I put that? In the bottom, or crisscross from where it is. Okay, what do I want to convert this to? Well, I want to convert it to eggs. Do I have some type of relationship that includes eggs over cookies or cookies over eggs? Okay, and the answer is yes. I just got this conversion factor from our recipe. So all I need to do is put in these numbers right here. So 4 eggs and 76 cookies. All right, so now cookies is going to cancel out, and it's going to leave me eggs. So when I do this math, it's going to give me how many eggs. So I'll just grab my calculator. So now I can calculate this. So I have 114 times 4, and all of that is over 76. That's going to give me 6. Okay. So in order to do this recipe, I need 6 eggs. Now I could do this with all of the other ingredients that are in this recipe. Now that I know how many eggs, I could go back and I could calculate how much flour I need. Once I get that, I can calculate how much sugar I need. And I can convert this recipe, all of these measurements in this recipe, to make 114 cookies. Okay, it may take some time, but you can do it. It is possible to do that. And if you're running a catering business, you certainly, if you get an order for 114 cookies, you're running a catering business, you certainly do not want to make 152, because you're just baking your profits, okay? And you don't want to do that. You want to profit as much as you can. So you want to make sure that you only cook exactly what you need. All right, so another question, how many cookies could be made if you had 3.5 cups of flour? So let's say that you wanted to bake cookies for a party, and you have this recipe, and you have plenty of salt, you have plenty of butter, plenty of sugar, plenty of vanilla, you have a box of baking powder, and you have a dozen eggs, but when you looked in your pantry, all you had was 3.5 cups of flour. Okay, so that flour is what's called your limiting reagent, your limiting factor. Let me write this down here. Limiting reagent. So you have an excess of everything else. You're limited by how much flour that you have, because you only have 3.5 cups. Okay, and we have those in chemical equations as well. So we can use information in our recipe to figure out how much we can make and how much of the other ingredients we're going to need. All right, so I'm going to start off with my given 3.5 cups of flour. Okay, and I'm going to set this up as a conversion. So I'm going to put that over 1. And I need the relationship between flour and cookies because I want to get rid of flour here. And I want to know how many cookies I can make. All right, so on this previous question, I already set up my conversion factor. And on this question, I'm showing you how to get your conversion factor once you know what you need. So I need the relationship between flour and cookies. So I'm going to go back here and look at this recipe. And for 5 cups of flour, it's going to make 76 cookies. Okay, so it's 5 to 76. So I'm going to go back here and write this down so I can remember that. So 5 cups of flour to 76 cookies. So that is the conversion factor that I'm going to need. All right, so cookies and flour. So what's in front of cookies? 76. So I'm going to put 76 here and 5 cups of flour here. All right, so cups of flour. It's going to cancel cups of flour, and I'm going to be left with cookies. And that's what I want because here it says how many cookies can I make. So I'm going to go ahead and write down the unit that I'm going to have for my answer, and then I'm going to just calculate this. All right, so grab your calculators again. We have 3.5 times 76, and that's going to all be divided by 5. That's going to give us 53.2 cookies. 53.2. All right, so how many sig figs do we need? We only need 2 sig figs. So we can drop this 2 off. So we can bake 53 cookies. 53 cookies. All right. And we could do that, keep using our recipe to do that. So here we have a chemical equation. Now, chemical equations are exactly like recipes. We have solid calcium chloride. All right, so calcium chloride, CaCl2. How do we get calcium CaCl2 from calcium chloride? Well, I reviewed that yesterday, but let's review this again today. So calcium is a +2 charge. Chloride is a -1 charge. We get those from the periodic table, the groups that they're in, their placement on the periodic table. So since these numbers aren't the same and don't cancel each other out, then we have to swap and drop. So this 2 is going to come here. This 1 is going to come here. And then so when we write our formula, remember we don't write 1s. So we don't write that 1 for calcium. Then we put the chloride here and we write the 2. So that's CaCl2 for calcium chloride. All right, same thing with sodium bicarbonate. Here we have our sodium, which is a +1, okay? And then bicarbonate, that is a polyatomic ion, also called hydrogen carbonate. So that's HCO3, that's a -1 charge. So since these do cancel each other out, then all we do is smash them together. We don't need any subscripts or anything. All right, so when we react calcium chloride with sodium bicarbonate, you would not know that we get all 4 of these because when we were talking about double replacement reactions, we talked about these 2 things replacing each other. Okay, so you would think that you're going to get sodium chloride, salt, which is right there, and calcium bicarbonate, but you do, but it continues to react. So the sodium chloride reacts with the calcium bicarbonate, and you produce these. So it's a reaction that doesn't stop after the initial reaction. There's what's called intermediate steps to this. But anyway, we get these 4 products in this reaction. Okay, so if we look at these, we can see that when we balance this equation, that we need a 2 here and a 2 here to balance this. Now, when we're talking about balancing equations, I didn't tell you what those 2's were. To what? To atoms, to teaspoons. Well, what that is moles. So we have 1 mole of calcium chloride combines with 2 moles of sodium bicarbonate to produce 2 moles of sodium chloride, 1 mole of calcium carbonate, 1 mole of water, and 1 mole of carbon dioxide. Now remember, moles is just a unit of measurements, just a way to measure compounds in chemistry. Just like when you're looking at a recipe, cups is a way to measure flour. Teaspoons is a way to measure vanilla. And as a matter of fact, we could convert all of these to cups. Instead of teaspoons of vanilla, we can convert it to cups of vanilla. Okay, it's going to be like a fraction of a cup, but we could do that. Teaspoons is just a way to measure smaller fractions in recipes. So moles is the way we measure things in chemical reactions. And when we look at these comparisons, we call that a molar ratio. So the molar ratio of this balanced chemical equation is 1 to 2 to 2 to 1 to 1 to 1. And I've written that right there. So just like a recipe, a food recipe, we could double this reaction. So instead of 1 mole of calcium chloride, what if I double that and put in, or instead of 2 moles of sodium bicarbonate, what if I supplied 4 moles of sodium bicarbonate? What quantities could we get out of here? Well, if I double this to 4, which is what this is, then I double this one as well. So I'm going to get, let me get my pen, 2 of these. And if I double this quantity right here, I'm going to get 4. And then doubling this one will give me 2, 2, and 2 on down the line because there's ones here. Well, if I take this quantity and multiply it by 8, then I would get how much here? 16. How much here? 16. And then the rest of these would be 8. 8 to 8 to 8. Okay, so you can double it, quadruple it, you can septuple it if that's even a word. You can multiply by any factor. Okay, and so why does that keep coming up? So why is this important in chemistry? It's important because if I know how much sodium bicarbonate that I put into this reaction, okay, let's say I have 100 grams of sodium bicarbonate that I put into this, I can calculate how much of calcium chloride I'm going to need. And I can calculate how much sodium chloride I'm going to get, how much calcium carbonate I'm going to get, how much water I'm going to get, and how much carbon dioxide I'm going to get. Just like here, if I know I got 67.2 liters of carbon dioxide, I know how much water I got, I know how much calcium carbonate I made, I know how much salt I made, I know how much sodium bicarbonate I'm going to need, and I know how much calcium chloride I'm going to need to get this. So with these molar ratios, I can calculate any one of the other items that are in this chemical equation. That is called stoichiometry, and that's all it is. It's not hard to do. It's just conversions. You're just converting this into any one of those others using one conversion factor. That's all you have to use. Now, it's not really as easy as that because, let me tell you why. Let's say in our problem, like this one, we're given liters, okay? We're given liters right here, 67 point, what was it? 2 liters. But the question wants to know, how many molecules of sodium bicarbonate am I going to need? Well, this is where the mole map comes in. We've already studied the mole map. It's not very hard at all. So what we're going to do is take this 67.2 liters and convert it to moles. Because remember, moles are here. Now, once we're in moles, we convert it to either grams or particles. Okay, so the key in chemistry is to convert everything to moles, because once it's in moles, we can convert it to anything else. So that's why in these chemical equations, it's important that you start off with a balanced equation, because once you start off with a balanced equation, you know how many moles it takes or it produces. Because once we're in moles, we can calculate particles, we can calculate grams, or we can calculate liters. Okay, so that's why it's important to remember this mole map. Okay, so that's as easy. So it's one conversion, converting between what you have in your chemical equation. So you convert it to another one, and then you use the mole map to convert to whatever units you need for your answer. Okay, so let's look at an example problem. It says, how many moles of water can be produced if 0.85 moles of sodium bicarbonate is combined with excess calcium chloride? So this is like our recipe where we only had 3.5 cups of flour. Okay, here's our 3.5 cups of flour right there. And we have excess of everything else in the recipe that we need. But for this question, we're only concerned about the calcium chloride. Okay, so this is excess. So do you remember what we call the 0.85 moles? That's going to be your limiting reagent. This is going to limit how much can be produced or how much is needed. Okay? All right, so let's get this rolling. Let's use our glues. We're going to start off with our given. So we have 0.85. We're going to list this out, moles of sodium bicarbonate. So that's going to be the NaHCO3. And it asks how many moles of water. So how many moles of water, and that's H2O. Now, since we're not balancing this equation, and we already have a balanced equation up there, we don't need to write water as HOH, because I remember I told you from this day forward, if you're going to balance an equation, or if you're using an acid-base neutralization, when we get to acids and bases, you're going to write water as HOH. But since the equation's already balanced, we don't need to do that. We're going to write it as H2O. Okay, so now we just need to look at the molar ratio between sodium bicarbonate and water. Now I'm going to go ahead and get this conversion factor set up before I start. So it's going to take 1 mole of water is equal to 2 moles of sodium bicarbonate. Okay, so that's the conversion factor that I'm going to need. We're converting from sodium bicarbonate to water. All right, so we're going to start off with our given. So that's 0.85 moles of sodium bicarbonate. We're going to put that over 1. Okay. All right. And what are we looking for? Moles of water. So the good thing about this is on our mole map, we don't have to convert to grams, particles, or liters. We're staying at moles. All right. We're going to start off easy. All right. So what unit do I want to get rid of? I want to get rid of moles of sodium bicarbonate. So I'm going to put that in the bottom because I know I'm going to get rid of it. What do I want to convert it to? That's going to be moles of water. So do I know a conversion factor that I can use to get to moles of water in one step? Right there it is. We wrote this down from our equation. All right. Oh, this is supposed to be moles. I forgot to put the mole in there. All right. So 2 moles of sodium bicarbonate is equal to 1 mole of water. And how do I know that? I got it from my equation right here. And remember, if I don't have any numbers written here, it's 1. We just don't write the ones. All right, so cancel what you can cancel. I can cancel moles of sodium bicarbonate. That leaves me with moles of water. Is that what I want for my answer? And the answer is yes. So now I can stop and do the math. So I'm going to pick up my calculator. Okay, and it's going to be 0.85 times 1, all divided by 2. That's going to give me 0.425 as my raw answer. How many sig figs do I need? Okay, that's 2 sig figs because leading zeros don't count. So this is going to be 0.43 moles of water that can be produced. Booyah, that's all there is to this. Now, we can take that moles of water and we can convert it to grams of water. We convert it to liters of water if it was a vapor, or we can convert it to particles using the mole map. But we started off easy and just kept it as moles. Okay, one more example. How many grams? Okay, so now we have to go to grams. We have to use this mole map to go to grams. How many grams of sodium chloride can be produced when 41.5 grams of sodium bicarbonate completely reacts? Okay, so here's our given. I'm going to write it down. 41.5 grams of sodium bicarbonate. Oops, I forgot my A in sodium. Okay, and we're looking for grams of sodium chloride. Okay, so we're looking for grams of sodium chloride. All right, so this is a little more complicated because remember I said these ratios in this equation right here are molar ratios. Well, it's given us grams in the problem. So we're going to have to convert these grams to moles. And then I'm going to have moles of sodium chloride that I'm going to have to convert back out to grams. So we're going to have to use the mole map twice. Once to go from grams to moles, and then go back out from moles to grams for our answer. Not a big deal. No sweat. Oops. Okay, so let's get this started. So 41.5 grams of sodium bicarbonate, okay, over 1. I know this is going to be long, so I drew that line out there. Okay, so we need to get rid of grams of sodium bicarbonate, and we need to convert that to moles because I have to have everything in moles because this relationship in our equation is in moles. Okay, so sodium bicarbonate. Now, how do I do that? Let's look back at the mole map. How do I go from grams to moles? What do I use here? So if you'll remember, this is the molar mass of whatever compound that we're using in the problem. So we're going to have to calculate the molar mass of sodium bicarbonate. So let's review that. Remember the molar mass, you're just adding up the masses of 1 mole of each element that is in this compound. So we have sodium that's in this compound. We've got hydrogen in this compound. We've got carbon in this compound. And we have oxygen in this compound. So how many moles of sodium are in this compound? 1. How many moles of hydrogen? No subscript, so that means 1. How many moles of carbon? No subscript, so that means 1. How many moles of oxygen? We have a 3 subscript, so that means 3 moles of oxygen in that compound. Then we're going to multiply this by the molar mass of each one of these elements. So the molar mass of sodium is 22.99, I believe, if I'm remembering correctly. So I'm just going to move back here just a little bit so I can grab my periodic table. And there's not a periodic table in the book I grabbed. That's okay. We'll just look it up. All right, so sodium 22.99. Yep. Okay. So let's go back here. Back nab it. And do 22.99. All right, hydrogen I know is 1.01. Okay, carbon is 12.01. And oxygen is 16. I know those for a fact from the top of my head. All right, so 1 times 22.99 is 22.99. 1.01, 12.01, and 16 times 3 is, I'm going to make sure I don't make a mistake here, 16 times 3, 48. All right, so add all of this up, and that's going to get you the molar mass of sodium bicarbonate. Okay, so 22.99 plus 1.01 plus 12.01 plus 48.00, 84.01. Okay, so 1 mole of sodium bicarbonate is, what did I say? 84.01 grams. All right, cancel what you can cancel. We can cancel out grams of sodium bicarbonate now. Now we have moles of sodium bicarbonate. So once we're in moles, we can convert this from sodium bicarbonate to sodium chloride using the molar ratio from our chemical equation. All right, so we want to get rid of our moles of sodium bicarbonate. Okay, we're going to convert this to moles of sodium chloride. Okay, so from our equation, it's a 2-to-2 relationship. 2 moles produces 2 moles. So now we can cancel. Now we've got ourselves into moles of sodium chloride for the unit. All right, so we're almost there. We want grams of sodium chloride, so we have to do one more conversion. We want to get rid of moles of sodium chloride, and we want to convert this to grams of sodium chloride. Okay. All right, so how do we do this? How do we go from moles to grams? Again, looking at the mole map, we're going to have to use the molar mass. So I need the molar mass of sodium chloride. So in sodium chloride, I have 1 mole of sodium, and I have 1 mole of chlorine. Well, 1 mole of sodium is, we looked that up just a moment ago, 22.99 grams per mole. Chlorine is 35.45. Okay, so we have 22.99 plus the 35.45. Add those together, we get 58.44 grams per mole. So for 1 mole, it's 58.44 grams. All right, cancel what you can cancel. Moles, we're in grams, so we're there. All we have to do is calculate. So let's pick up our calculators. We're going to have 41.5 times 1 times 2 times 58.44. And all of this is over 84.01 times 2 times 1 times 1. We're going to get, I'm going to write it right here, 28.86870611. Now we don't need all those numbers. How many sig figs? We're given 3 in our problem. So here's 1, here's 2, here's 3. So we're going to look at this 6. Does the 6 round the 8? It does. So our final answer is 28. That's not an 8. 28.9. What are our units? Grams of sodium chloride. Simple, easy, breezy. All right, and so that's it. So now you know how to do it. All that's left to do is practice this, practice, and you can get perfect at doing this. This is called stoichiometry. All right, so that's it for the notes. Make sure you slap that like button right across the face. Click that bell notification and subscribe so that you know when I put videos on YouTube, if for some reason I don't get them immediately up on Canvas.